find the metric of the line element, we must follow this equation here, where these are the coefficients. The coefficients go into this matrix. We match the coefficients to find this is our lovely diagonalized matrix. So now it's very easy to find the inverse because it's just a reciprocal of the diagonal elements. For v squared, we're given this equation for v squared. Their values are a, b, c for v mu. We plug everything into this equation to get this final answer. For part B, it's the exact same procedure for the metric and inverse metric. The only difference is we've got minus dx dy. Now dy dx and dx dy are equivalent. They've been summed together. They're two terms. We must halve the coefficient here, and then we get this for the metric. The inverse metric is as follows, and we get that. And now we compute v squared, same procedure again, just there. And then for question 2, part A, this is essentially the Kronecker delta with the free indices. There's no free indices, so it's just a trace of the Kronecker delta in d dimensions, where d is the dimension of the manifold. And then in part C, we expand to find that we get two equivalent terms, which is the difference between two equivalent terms is 0. In part D, we expand everything to find that we get this. We get the dot product between two scalars minus, again, the dot product between two scalars. Now, these two scalars commute because they're scalars, so the difference is 0. And then here it's a bit fiddly, but in the second term, we notice we can contract the indices and get this for our metric. And then look at that, we get a dot b. So the difference between two equivalent terms is 0. Anything multiplied by 0 is 0. That's our answer. In question 3, we're trying to show that these are the non-vanishing Christoffel symbols. So again, we look at the line element, we find the metric, the inverse metric, we follow this equation for the Christoffel symbols to verify that yes, these are indeed our non-vanishing Christoffel symbols. So then part B, when we've got the geodesic equation, we plug in the non-vanishing Christoffel symbols to find that these are our two components in terms of theta and phi. So then in part C, when we're on a meridian, phi is fixed, so the derivative is equivalent to 0, and we get this set of solutions for theta. And then we're at the equator, theta's fixed, so theta dot, derivative of theta is 0, and we get this set of solutions here. And then so the non-vanishing Christoffel symbol, oh dear, no, that's wrong. Riemann tensor, yes. So we're trying to show that the Riemann tensor vanishes on a plane, on a flat plane, and indeed the Christoffel symbols, they all vanish. The Riemann tensor is composed of, well, all of our vanishing Christoffel symbols, so it does indeed vanish itself.